Today we are going to discuss about energy spectral density and power spectral density. So these are the two spectral density that we are going to discuss. I assume that you know what is energy and what is power, what is the difference between energy and power from your physics classes. Now let me start defining what is spectral density when we come to communication or when you come to signals that is propagating. In terms of signal, what is density, what is spectral density? You know what is spectrum of a signal. When you say a signal, suppose st is a signal, s as a function of t, st is a signal, then we can represent any signal, any function. St is a signal, it can be represented as a function of time. Any function can be represented as a Fourier series. So st can be represented as a Fourier series. By Fourier series, what you mean? So let me give you an example. St is equal to a1 cos omega t plus a2 cos 2 omega t plus a3 cos 3 omega t. This way it goes up to infinity number of terms or any finite number of terms where you terminate. Now if you look at these terms, first is cos omega 1 cos omega t, then second is cos 2 omega t, third is cos 3 omega t, etc., which means the frequencies are at omega. Frequency means angular frequency, which is 2 pi f, or 2 per 2 is constant, pi is constant, so f is different. So frequencies are at omega or f, 2 omega or 2f, 3 omega or 3f. These are the frequency where the signal component exists. At other frequency between omega and 2 omega, suppose 1.5 omega, there is no signal component. So the frequencies at which signal exists is determined by this. What is the component of signal, or what is the amount of signal that is there? That is A1 or A2 or A3, that is the amplitude of the signal, maximum amplitude of the signal are corresponding to that frequency. Now, based on that, this is called the spectrum. Spectrum means at which frequency, what is the maximum amplitude of the signal. That is what is given by the spectrum. So the frequency will be in x-axis and spectrum or the amplitude will be in y-axis. Now based on this, once we know this, and then what is spectral density? So let us define spectral density. Spectral density is, this is a fundamental concept in signal processing, communication system, etc. This, the signal processing, it refers to the distribution of either power or energy of a signal across different frequencies. So signal will have different frequency components. Across these frequency components, what is the power or what is the energy? So how the energy or power is distributed across different frequencies, which means if I draw a graph with x-axis representing the frequencies, y-axis representing the power or energy, then that graph shows the spectral density of energy or power. So based on this definition, we define energy spectral density or ESD. In short, energy spectral density is called ESD. It is a measure of the energy content of of the signal at different frequencies. Which means if I draw the graph, in the x-axis we have the frequency, in the y-axis we have the energy, then that graph represents the energy spectral density. That is a graphical representation of the energy spectral density. So this will give us information about the signal's energy distribution over the frequency domain. So remember that it is important to remember that the spectral density, when we say spectral density, we are dealing the frequency domain part of the signal, not in the time domain. So we are not in the time domain, we are in the frequency domain, because the graph is between frequency and energy or signal. Similarly, the, the power spectral density, this measures the power content of the signal at different frequencies, or the distribution of power content of the signal across different frequencies. So this provides information about power distribution over the frequency domain, like energy density, energy distribution, power spectral density, power distribution. Next. Next. Now, what is the importance of spectral density in electronic systems that we are considering? What is its importance? Why we should know how the energy or power is distributed across frequencies? First is it helps us in signal analysis, analyzing the signal, because the spectral density analysis will enable us to understand the frequency components present in the signal. Once you look at the graph, from that graph you can say that at this frequency, this much of energy or power is there. So frequency components, and at this frequency there is no power or there is no energy. So from that we know what is the component of frequency which is active. So once we know that, it will help us identifying the dominant frequencies. How? Because the frequencies where the energy or power is more, that frequency is dominant. Then noise sources, we know that over this frequency band, or our original signal is of this frequency band. Like suppose sound. In the sound, it is from 2 kilohertz. So between sorry 20 to 20 kilohertz. So in this range it should be there. If it is beyond that, if some component is there, that is the noise source. Or even within that range, if there is a peak in the energy, or there is a peak in the power, so that peak usually indicates a noise. So this is how you get. Similarly, interference from other sources. So you can see that once you look at the spectrum, power spectral density spectra, or the graph, there you can see that two graphs are superimposed. So if two graphs are superimposed, or more than two graphs are superimposed, one graph is your original signal, other graphs are from the other sources. So those are interfering signals. So signal analysis, it helps us in signal analysis. Next. It helps us in characterizing the system, because you can examine the frequency response, how the system is responding to the frequency, then what is the bandwidth over which it is working properly, and what is the noise behavior. So you can characterize the system accordingly based on frequency response, bandwidth, and noise. This information we can get from this plot. Next. Then in designing the filters, that is another important aspect, because we will know which are the required frequency component, or which is the required frequency band. Once you look at this graph, then you can look at which are the not required. So where the energy strength is high, that is the required band, mostly high. Then beyond that, it is not required. So that we can filter out which frequency components are not required. So those components can be filtered out, others can be enhanced. Next. Next. Fourth is in communication system, all types of communication system, digital or analog. This is crucial to optimize the bandwidth utilization of the system, to minimize interference, and to improve the signal quality. So these are the three things for which it is important. What are these three things? Your bandwidth utilization, optimized utilization of bandwidth, minimizing the interference, and improving signal quality. Next. Then in power systems, beyond this communication is our interest. Power system is particularly electrical power. So there it is important to analyze the power quality that we are getting. So how do you analyze the power quality? Because you identify what are the harmonic components. As you know, how the power supply is 50 hertz. So beyond 50 hertz, suppose you have 100 hertz. With 50 hertz, you have 100 hertz, 200 hertz, 150 hertz. So those are the harmonic components available. So you can identify them from this graph. Then you can ensure stable and efficient operation of power systems once you know that. Next. Then doing a noise analysis in the communication system or power system, any system where you are using it, then it plays a important role because you can quantify noise characteristics in the electronic system. Once you quantify the characteristics, then you can reduce the noise and you can develop mitigation strategies. Mitigation strategy means how to avoid or minimize the noise. So those strategies you can develop automatically. Next. And then this is important in research and development because nowadays people are developing technologies, advanced technologies to improve system performance. To improve system performance, first you have to know what is the system, how the system is working. That you can know from the knowledge of power spectral density or energy spectral density. Therefore, it is important in research and development. Next. Next. Now we'll discuss about energy spectral density. We'll come to its specific definition and have a conceptual overview of spectral density next. So this ESD measures the energy content of the signal at different frequencies. This is the definition. Based on this definition, it will provide you information about how the signal's energy is distributed across the frequency domain. In the frequency domain, how the energy is distributed. So these are two important points. Now, how you will calculate this and how mathematically you will represent this energy spectral density. So this is typically calculated by using Fourier transform or discrete Fourier transform. So you should know what is Fourier transform, what is discrete Fourier transform. If you have a continuous time signal xt, then you will square the magnitude of its Fourier transform. So the Fourier transform, you take the Fourier transform and square its magnitude. That will give you the energy spectral density S subscript XX. So S subscript XXF is the uh, energy spectral density. Next. So ESD energy spectral density is S, no, back, is S subscript FF, which is the absolute value of XF square. So take XF, take its absolute value, square that. XF is the Fourier transform of XT. XT is your continuous time signal. Its Fourier transform is XF. Take the XF, take its absolute value because that will be complex in nature. So take its absolute value to get the real part, then square it. So that gives you the EST. Next. 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 Then if you have a discrete time signal xn, then the EST is obtained by taking DFT or discrete Fourier transform and squaring its magnitude. Next. So here SXX, which is the energy spectral density, that will be the absolute value of xk. Xk is the discrete Fourier transform of xn. So take its absolute value, square it, That gives you the energy spectral density. Next, next, next. Now, how do you physically interpret it and what are its significance? First is no, ESD represents the energy contribution of each frequency component in a signal. So, this is a physical interpretation. Second is this helps in identifying the dominant frequency components and their relative energy contributions. Next. Higher values of ESD that will indicate higher energy concentration at that frequency. So the frequency where ESD is high, that frequency at that frequency energy concentration is high. Next. ESD is providing us insight into signals characteristics like bandwidth. So how it provides you bandwidth requirements and characteristics, because you can see the ESD curve there, the portion where it is high, ESD is high, that is the required bandwidth. Where it is low, that is not required bandwidth. That is outside the bandwidth. So you get bandwidth requirements. Similarly, frequency dependent behavior that also you get, because at which frequency these are present, from that you will know which are the frequencies affecting the system. So frequency dependent behaviors also known. Next. How it is related to the Fourier transform, we have just seen now from the definition. The Fourier transform decomposes a signal into frequency components, while ESD quantifies the energy distribution at each frequency. So this is the main relation. So ESD is obtained from the Fourier transform by squaring the magnitude of the Fourier transform. Next, next. Then where it is applied, there are many applications. We'll see some of the applications and cases where it is applied. One is audio signal analysis. This can reveal the energy distribution in audio signal, like any other signal. On audio signal also, it reveals the energy distribution. That helps in audio processing and equalization. Once you know the energy distribution, you can develop the equalization process. Next. Then in radio frequency signal analysis, this is used to analyze the radio frequency signals, identify which frequency components are present, and optimize the communication system accordingly. Once you know which are the frequency components, you can design the antenna or you can design the system accordingly. Then power spectrum analysis. This helps in power spectrum estimation, and once you know power spectrum estimation, this allows you for power analysis in different frequency bands. Next. Then finally, in wireless communication systems, since it is applicable in RF systems, so in naturally it will be applicable in wireless communication system. This is vital for wireless communication system to optimize the frequency allocation, to detect any interference present, and to improve the signal quality. Then sensor data analysis. This is used to analyze the signals from sensors in different domains like in the environment, in health application, biomedical applications, where you employ sensors, electronic sensors. So from the electronic sensors, when you collect data, you should know how much energy is there, because those data are very feeble data. Their energy content is very small. So that you should be one, unless you know you have the idea of energy content at different frequencies, they will be masked by noise. So that is why it is important in sensor data analysis. Next. So with that, we come to the end of energy spectral density. We will now consider the power spectral density. Both are almost same. In one case we have energy, other case you have power. Power is energy per time, unit time. That is what is power. So definition and conceptual overview. Power spectral density measures the power content of a signal at different frequencies. It provides information about how the signal's power is distributed across the frequency domain. So these are the definitions. First is the definition, second is the explanation of the definition. Then how to calculate this? PSD is power spectral density. This is typically calculated using Fourier transform or discrete Fourier transform. These two are going to be used. You have to be in frequency domain. If you have a continuous time signal xt, its power spectrum, its Fourier transform you will take, then from the Fourier transform find the autocorrelation function, then find the PhD. PhD is SXX. XX is the subscript, so S subscript XXX, that is the PhD, and that you will get from the autocorrelation. Next. So the PhD is equal to Fourier transform of the autocorrelation. So take the autocorrelation, take its Fourier transform, then find that gives you the power spectral density. So first you have to take the autocorrelation. So autocorrelation of the signal, find out the autocorrelation of the signal RXX. RXX is the autocorrelation of the signal. So from the autocorrelation, you will find out what is the power spectral density. So this is the difference between these two. There you are finding for the energy, you are finding the Fourier transform and squaring it. Here you will first find the autocorrelation for the power spectral density. First find the autocorrelation, then take its Fourier transform, that gives you the power spectral density. Is a similar case for the discrete time signal. So DFT of RXX gives you the PhD. Next. RXX is the autocorrelation of the sequence of Xn, Xn being the discrete time signal. Next. Now, the PhD represents the power contribution of each frequency component in the signal being analyzed. It helps in identifying the power distribution at different frequencies and their relative contributions. Which frequency is contributing to more power, which frequency is contributing to less power. That relative contribution is obtained from PhD. High value of PhD indicates higher power levels at that frequency. If at one frequency the PhD is of high value, at that frequency power level is high. If at one frequency PhD is of low value, at that frequency the contribution is low, power is low. The PhD provides insight into power characteristics of a signal. So once you know what is the power characteristic, then you can do a analysis of the signal. You can design the signal, make changes to the signal. So analysis and synthesis, or analysis and design of the system, is helped once you have information of PhD. Next. Next. Now, how it is related to autocorrelation function RxX. PSD is closely related to autocorrelation function because you are obtaining it from by taking the Fourier transform of the autocorrelation function. Next, autocorrelation function. What it does, it quantifies the similarity between a signal and a delayed version of the signal. So take a signal, take a delayed version of it, then find out their correlation or similarity, that gives you the autocorrelation of the signal. A PhD is obtained by taking the Fourier transform or the DFT of the autocorrelation signal or autocorrelation function. So that is, so and then we'll consider what are the applications and some cases where it is applied. So applications and use cases. The main application is in wireless communication. So PhD analysis is important for analyzing as well as optimizing wireless communication systems. So in this analysis or optimization, what are the parameters which are considered? The parameters that are considered are signal modulation, estimation of the channel, and avoiding the interference. So mitigation of interference. These are the characteristics which are considered. Then second application is managing the spectrum management. So PSD will help us in efficient spectrum allocation because we know which frequency components contain maximum energy. We will allocate those frequency components and avoid other frequency components for that signal. So that helps in spectrum allocation and avoiding the interference in the wireless communication or wireless networks. Next. Then signal integrity analysis of the signal integrity. The PhD is used in signal integrity analysis to assess the power content and potential noise sources in high-speed digital systems. Well, so this signal integrity analysis is useful in high-speed digital communication system or in all high-speed digital systems. Signal integrity is an important concept where you require to know what is the power content and what are potential noise sources. Those you can get from PhD analysis. Then audio and video processing. So this is employed in both audio and video processing for equalization of signal, to remove noise, to improve signal quality. So these are important applications. Then radar and sonar systems, they utilize to analyze echoes, particularly they work on the principle of receiving echo and analyzing it. So for analyze and echoes are of lower power content. So they are used to analyze echoes, detect targets. By analyzing echoes, you will detect targets, so detect target detection and optimizing the signal processing algorithms used in the radar and sonar systems. Now, what are the key differences between them? Let us look at the mathematical formulation. ESD, energy spectral density. For that, mathematical formulation is take the magnitude of Fourier transform or DFT signal and square it. Right. So ESD is xf mod square or absolute of xf square or absolute of xk square if it is a discrete time signal. Next. Next. But if you look at the power spectral density, it is on the Fourier transform or DFT of autocorrelation function of the signal. So this is PhD's Fourier transform of RXX tau or RXXM. If it is discrete time signal, RXXM. If it is continuous, RXX tau. Next. Then energy spectral density. Next. This measures the energy content at different frequencies, quantifies the energy distribution and concentration across the frequency domain. Next. It is useful for analyzing energy contribution of different frequency components in a signal. Next. 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 Similarly, power spectral density measures the power content at different frequencies. Next. Quantifies power distribution and intensity across frequency domain and provides information about power contribution at different frequency components in a signal. Next. Then practical implications. Energy spectral density is useful for analyzing energy consumption in a signal or system. Important is this: how much energy is consumed by the signal or system. For that you will get from energy analysis. So it helps in identifying energy intensive frequency components which require specific attention. Those frequency, which means the frequency components. So those frequency components which require specific attention in system design and optimization, those will be identified by identifying which are energy intensive frequency components. So this is commonly used in applications where energy efficiency is a concern. So like low power electronics, like your mobile phones, battery powered devices like vehicles, electrical vehicles, even mobile phones, laptops, and renewable energy systems. Next. Now let us come to the power spectral density. This is useful for analyzing the power consumption and power distribution of a signal or system. It helps in identifying frequency components with high power levels, which may impact system performance, interference, or signal quality. This is used in applications where power management is important, like interference avoidance, signal integrity, crucial, like systems like communication systems, power systems, high-speed digital systems, they use PST. Next. Now, how you will measure them? So, measurement techniques. They use Fourier transform based methods. Let us start with this Fourier transform method based methods, because in both the cases we are taking Fourier transform. In one case we are taking the Fourier transform of the signal, in other case it's correlation function, autocorrelation function. So on the frequency transform, or sorry, the Fourier transform, this is widely used method. So it calculates the spectrum of the continuous time or discrete time signal by converting it from time domain to frequency domain, FT, that is the function of Fourier transform. The magnitude of Fourier transform provides the spectral density information. Next. Next. Then we use periodograms based methods. What is periodogram method? Periodogram estimates the spectral density by computing the squared magnitude of the Fourier transform of a finite length segment of a signal. So you take a signal, then consider a finite length segment of the signal. For that finite length segment, you take the Fourier transform, square it, that gives you the periodogram of the signal. This directly applies to Fourier transform to signal segments without any further processing. So that is why it is important. The periodogram, this is simple to implement, and it can have limitations in terms of resolution, variance, etc. Because directly you are working over a one segment. Second is called Wells and Bartlett methods. So Wells method and Bartlett method. Wells method, in this method, this improves the periodogram by dividing the signal into overlapping segments. So instead of taking one segment, you take many segments, and the segments are overlapping with each other, and then you average the periodogram. So for each segment you find out the periodogram, average the periodograms of these segments. That is what is Wells method. Next. Now because of the overlapping, this will reduce the variance of the spectral estimation. So there won't be a high variance. Variance will be reduced because of overlapping of the segments. And that improves the resolution, because the variance is reduced, the resolution will improve, and ultimately it will result in reducing the noise effect. On the other hand, this provides a trade-off between frequency resolution and variance reduction. So it has to provide a trade-off. Frequency resolution and variance reduction, there has to be trade-off. So if you have good frequency resolution, you will not have good variance. If you have good variance, you will not have good frequency resolution. Then Bartlett method. Bartlett method is a variation of Wells method, and in this you are taking many segments, but these segments are not overlapping with each other. So in the Wells method, segments are overlapping. Here they are not overlapping. Since they are not overlapping, so they will provide a high frequency resolution, but there will be more variance compared to the Wells method. So frequency resolution increases, variance decreases. So the variance will be increased. Next. Then, and there are parametric methods. So after these two methods, there are parametric methods. These methods assume that the signal can be modeled by a specific mathematical model. So you can employ a mathematical model, specific mathematical model, like autoregressive method or moving average model. So these models can be employed for the analysis. So that is parametric method. The parameters of the model uh, are the estimated technique using techniques like Euler-Walker or Borg methods. Unless you know this, you can avoid this. Don't worry about this. These methods. Next. The model parameters are then used to estimate the spectral density. Non-parametric methods are they do not assume any specific signal model and estimate the spectral density directly from data. So that these are non-parametric methods. They include modified periodogram, a multi-tapper method, Pronis method. These are all. A Pronis method is the optimization technique. Next. Now, what are the advantages and limitations of these techniques, different techniques? If you have Fourier transform based methods, then advantage is simple, well-established method provides exact spectral representation. Limitation is it is limited to stationary signals, require a long observation of uh, back, 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 back. Ah. So this requires a long observation time for accurate results. So that is its limitation. For your transform methods, limitation is long observation time. Next, next, next. Then if you consider the periodogram based methods, next. Advantage is these are simple and straightforward implementations like Fourier transform. Limitation is they suffer from high variance and poor frequency resolution. Next. Wells Bartlett method. Next. Advantage is overlapping segments improve frequency resolution and reduce variance. Limitation is there has to be trade-off between resolution and variance reduction. So which because of that there can be spectral leakage. Next. Then spectral estimation techniques. They can handle non-stationary signals, provide accurate spectral estimation with fewer data. Now, what is stationary signal? What is non-stationary signal? Stationary signal is a signal whose statistical characteristics does not change with time. If the statistical characteristics like mean, variance, etc., of a signal changes with time, then that is a non-stationary signal. Now, limitation of spectral estimation technique is parametric methods. They rely on specific signal models. Non-parametric methods may be computationally intensive. These are the two parts. Then signal processing and communication. Uh, Noise analysis. For noise analysis, next. They help in characterizing noise sources in a signal or a system. What are the noise sources? They can be characterized. Spectral density of noise provides insight into frequency distribution and power contributions. Next. Forget this. Next. Next. Signal analysis using spectral density. They aid in analyzing and understanding the frequency components present in the signal. Next. Helps in identifying important signal characteristics like dominant frequencies, harmonics, noise levels, etc. Next. So you can find it using SSX, which is the spectral density. Next. Channel capacity bandwidth. Next. Here the spectral density analysis, they play a vital role in optimizing and utilizing the available bandwidth. Particularly, they measure how efficiently information is being transmitted in a given bandwidth. Higher spectral density allows for high data rates and improved channel capacity if you have high. And this is an example equation for the channel capacity C, which is equal to B into log 2 log 2, not into 2, log 2, base is 2. So log 2 into 1 plus log 2 of 1 plus SNR. So B is the bandwidth of the system, SNR is the signal to noise ratio. This is called Shannon's capacity formula. Shannon's capacity formula. Next. Then in filter design and spectral shaping, these are the spectral density helps uh, to modify or shape frequency response of a signal because you know the distribution. So filters can be used to attenuate or enhance specific frequency component once you know the you have the knowledge of spectral density. Next. So the transfer function for a filter is HF. This determines its effect on the spectral density of a signal. Next. Interference analysis and mitigation. Spectral density analysis aids in identifying and analyzing interference sources in communication systems. Helps in understanding the interference power and its importance on system performance. Next. This is given by interference spectral density, which is SIIF. II is the uh, subscript. Next. Next. The spectral density analysis helps in developing techniques to mitigate interference and improve system performance because you mitigate the interference, you can improve the system performance. Interference cancellation, frequency hopping. Frequency hopping means jumping from one frequency to another frequency. So you are working at one frequency, you go to the other frequency, which is not continuous. So two discrete frequencies, so to jump from one frequency to other frequency, that is happening. So then using adaptive filtering, so filter adapts itself depending on the system requirements. These are some strategies. Example is adaptive filter design. Next. And challenges and one challenge is limitation. We will find out what are the limitations. Stationarity assumption. So usually we assume that the signal is stationary, but in practice they may not be stationary. So that limits its applicability to non-stationary signals. Windowing effect, because of windowing choice of the windowing function. Windowing once you choose a window in the frequency. So choose a frequency band. If you choose a frequency band over which you are operating, that is called windowing. That introduces some effects. They can introduce artifacts and spectral leakage in the estimated spectral density. Next. Then the resolution versus variance trade-off. This we have discussed for measurement. Noise sensitivity. This also we have discussed. Spectral density analysis can be sensitive to noise. Then nonlinear system. So spectral density analysis may not fully capture the behavior of nonlinear system. Linear systems it is okay. Nonlinear system it may not capture it. So it requires advanced techniques for analysis. Next. So there have been advances like adaptive and robust methods. This is being researched. Compressed sensing of signals. This is being researched. Next. Then machine learning approaches. Nowadays, people are employing machine learning approaches, multi-sensor fusion. So collect data from multiple number of sensors, fuse them, and do a analysis. So, in the context of emerging technologies, where they will find applications. One is Internet of Things nowadays. This is a buzzword. So addressing challenges of spectral density analysis in IoT systems, they include resource constrained devices and interference management. Next. Then 5G and beyond. Next. So fifth generation, 5G means fifth generation communication systems, and beyond the fifth generation, which is sixth, seventh, etc. So expanding the spectral density analysis will support higher bandwidth, multiple access techniques like and advanced modulation schemes. Next. Then quantum communication. Don't worry about this. Next. So with that, we come to the end of our discussion on energy and the power spectral densities or spectral densities. Now we'll have a quiz to find out what you have understood. So what is the purpose of spectral density analysis in the electronic system? This is the question. Next. So to measure amplitude of a signal, to analyze energy distribution across different frequencies, to calculate phase shift of a signal, to determine the time duration of a signal. Time starts now. Next question. Next. Which mathematical representation is used to calculate ESD, energy spectral density? Autocorrelation function, Fourier transform, power spectrum, time domain representation. Time starts now. Next. Power spectral density is used to analyze noise sources in a signal, design filters to shape the frequency response, estimate energy content of a signal, determine the phase difference between two signals. Time starts now. Next question. What is a key difference between energy spectral density and power spectral density? ESD is calculated using Fourier transform, while PSD uses Laplace transform. ESD measures the power content of a signal, while PSD measures the energy content. ESD is used in communication systems, while PSD is used in power systems. ESD provides phase information of a signal, while PSD does not. Last question. Which technique divides the signal into overlapping segments and averages the periodograms to improve spectral estimation? Fourier transform, periodogram-based methods, Wells and Bartlett methods, spectral estimation techniques. Time starts now. Now that we have seen all the questions and the options, we'll go to the answer keys and compare your answers with the answer keys provided and the explanation next. So let us look at the answer keys. Answer to the first question is B, to analyze energy distribution across different frequencies. Why? Because spectral density analysis provides information about uh, of energy or power content of a signal at different frequencies. That helps in understanding frequency characteristics and distribution of a signal. Second question answer is B, Fourier transform. Explanation is the energy spectral density is calculated using the Fourier transform or discrete Fourier transform of a signal, where the magnitude of the Fourier transform of DFT, they are squared and they give the energy distribution across the frequencies. Question number 3 answer is design filters to shape frequency response. Power spectral density analysis helps in designing filters to attenuate or enhance specific frequency components in a signal that allows for spectral shaping and frequency response control customization. ESD measures the power. No, this is wrong. Actually, this is PSD. PSD measures the power. That answer is wrong. Power content of a signal, while ESD measures the energy content of the signal. So these two will be interchanged. So ESD quantifies the energy distribution at different frequencies, whereas PSD quantifies the power distribution. So ESD focuses on energy, while PSD focuses on power. So this question was wrong. ESD and PSD should be interchanged. Finally, fifth question is Wells and Bartlett methods, because these methods improve spectral estimation by dividing the signal into overlapping segments, calculating the periodogram of each signal segment, and averaging the periodograms to enhance frequency resolution and reduce variance. So with that, we come to the end of this segment. Next, we'll meet at 2 o'clock, where we'll start discussing about modulation. So that will be very important class. Don't miss that class. So that is more, in fact, that will be the most important segment. Blue tab. So that will be the most important segment. So with that, we come to the end of this session.